So we have three quantum states, 1, 2, 3, and the question is saying for each quantum state, let's do the third state. We don't have to do all of them, they're all the same. For each quantum state, let's do the third quantum state. Calculate the probability of the spin components measured along each one of the axes, x, y, and z. You remember how to find the probability component measurements, huh? Along x, y, and z. Yeah, probability is well, first start with it step by step. Yeah, it's the you have to operate. So if you were doing the z-axis, right, you'd have to operate on the wave function by the spin up state, right? So that means if you're finding the probability that it's spin up, you need to take your wave function and you need to operate on it with the spin up state along the z-axis, which is the 1, 0, which is the plus, right? And then after that, you're going to take the module of all that, square. That's the probability. And so now just plugging psi 3. I'm doing this for psi 3, but it's the same process for psi 1 and psi 2. So we get so now plugging that in, we get plus, and psi 3 is minus 4/5 plus I 3/5. And now if we operate on this, we will get minus 4/5. So spin up state will give us 1. Spin up, spin down state will give us 0. So we get minus 4/5 square, which will give us 16/25. And similarly for the spin down state, now we just switch this to the spin down state and same wave function. And this time spin down, spin up will be 0, and then we will get spin down is 1, and we will get, oops, sorry, wait, I switched this. We will get I 3/5, which would give us 9/25. So this was along the z-axis. If we do the other axes, it's the same thing. We just have to operate with a different spin function. So if we do, let's say the x-axis. Oops, let me change the color here. If I do the x-axis, then I would have to operate on the wave function. So if I'm doing the plus, so I'm working again on the third one. So this is gonna be 1/√2, right? This is the matrix along the x, plus 1 over root 2 spin down, and we're gonna operate with this on the wave function, which is minus 4/5, and then this whole thing squared. Okay, so when we operate with a spin up state, we get 1, and so we multiply the coefficients here, and this would be minus 4 over 5 root 2. Okay, and then when we operate with the spin up on the spin down, we get 0, so that goes away. And then likewise, when I do, if this highlighter works, when I do this on the spin up, this is 0, and when I do this on this, I get 1. So, and the coefficients are 3 plus 3 over 5 root 2i. Okay, and then I have to module that, meaning I would have to multiply by its complex conjugate. So minus 4 over 5 root 2 plus 3 over 5 root 2 times I minus 4 over 5 root 2 plus minus 3 over 5 root 2i. Okay, and this is the difference of two squares. So if I do this, we will get 16 over 2 times 5, 50, plus 9 over 50, right? So that's 25 over 50, so that's half. So you got that, Ben? What did you get for the first probability? So here we get half. And by the way, for the spin down, you don't really have to do that, because along the x-axis it has to be 1. So if it's half here, the other one is half. They have to add up to 1, right? It's 1 minus half, which is half. You could, and you should get the same answer. Okay, and I'm gonna just give you the answers for the y-axis, because it's the same process. You just use, actually let me write it down. So the y-axis, this would be spin up. We would operate minus I over root 2. So this is the matrix for the spin down, or the in Dirac notation, the bracket for the spin up, along the y-axis. And then this, we operate on the wave function. We're doing wave function number 3, so this is minus 4/5. Okay, plus I 3/5. Okay, and okay, so let's see what we get. So again, same process. Plus plus will get you 1, so that's minus 4 over 5 root 2. Plus minus 0, minus plus is 0, and minus minus will get us plus I squared is minus 1, and there's a negative, so plus 3 over 5 root 2. All squared. There's no complex here, so you could just square this. So what's this? 1 over 50? Yeah, 1 over 50. Oh, why is this going up here? Oh, so annoying when this happens. Anyways. Okay, so 1 over 50, and again they have to add up to 1, so the other one will be 49 over 50, or you could do the same thing. Okay, so okay, now part B is saying use your results to comment on the importance of the overall phase of the relative phases of the quantum state vectors. Okay, so to comment on the result, let me share with you the results because you have to know the results. So let's make a table here, okay, without having to do all of them, just to give you the answers for all of them here. I've worked them out, and let's do psi 1. So I'm gonna work out part B here. Okay, so I'm gonna make a table. So psi 1, psi 2, psi 3. Okay, and we're gonna do no, actually let me do it the other way. So psi 1, psi 2, psi 3, and I'm gonna have here P 1 in the minus x, right? Actually, let's start with plus x, probabilities. We're talking about probabilities. Plus y plus z minus x minus y minus z. Okay, so and let's write the numbers here. So let me make this a little bit. Okay, so for psi 1, this turned out to be 16 over 25, which means this one would have to be 9 over 25, and this one is a half, which means this one is a half, and the y was 49 over 50, which makes this 1 over 50. Okay, for side 2, so a plus is spin up, minus is spin down. Okay, for side 2, we have 16 over 25, which makes this 9 over 25. We have spin up along the x is half, minus half, half, and this was spin up 1 over 50, right, which makes this 49 over 50. And for side 3, this is the one we've calculated. So we got 16 over 25, which makes the other one 9 over 25. Half, half. 1 over 50 and 49 over 50. Okay, so what do we notice here? Well, notice that between psi 1 and psi 2, right, measuring along the x-axis was the same, measuring along the z-axis was the same, both spin ups and spin downs, while measuring along the y was actually reversed. Why? Because if you were to multiply state 2 by minus 1, you actually obtain, well, if generally speaking, if you multiply state 2, right, by minus 1, you actually obtain state 3. Right, so these two, they only differ by a phase. And what is that phase? Well, you could actually calculate that phase to be, if they're 180 degrees, right, cosine pi, turn this into complex I sine pi, because sine pi is just 0, right? I'm 180 degrees, so this is the same thing as e to the I pi, which is actually minus 1. So if I multiply state 2, in other words, by e to the minus pi, e to the I pi, sorry, I would get state 3. Right? And as can be seen by the table, between state 2 and state 3, since these only differ by a phase, e to the I pi, the results are identical. Right? Now, for states 1 and 2, different phases have different coefficients have different phases, and so you get different results. You get y, you get the same x, you get the same z, but you get swapped y. Okay, you have to flip them. So the point is, you have a relative phase, you have an overall phase going on between 2 and 3, and that's why you get the same result on the overall phase. This gets you same result. Whereas if you have a relative phase between 1 and 2 or 1 and 3, you get different results. That does it for this question.